So hello, everyone. Thank you so much for joining today's seminar. I'm David Rodriguez. I'm a system engineer at EPFL Space Center. And today we have the pleasure of counting with Dr. Gwendolyne Pascua. I hope I didn't butcher your name there. She's a physicist, and she's currently working as operations lead engineer, ground controller at the Biotechnology Space Support Center, or BIOTESC, as well as a senior research associate at Luzern University. BIOTESC, which, by the way, in full honesty, I didn't know existed prior to this, doing some research for this seminar, acts on behalf of the European Space Agency, advising scientists who intend to perform biological experiments in the Columbus Space Laboratory on board the International Space Station. And it also supports the astronauts conducting these experiments. Actually, Gwendolyne, I remember reading that you were in the Mission Control Center of BIOTESC when Thomas Pesquet flew to the ISS during Expedition 50, but correct me if I'm wrong, maybe. I don't know if you should always believe what you read on the internet.
Yes,
so,
it is that.
So we
it's
are
part of our project.
Awesome, yeah. So we are in for a treat with today's seminar. Before we start, just a few housekeeping rules. As Candy said, please mute your mics. Also, the video stream is being recorded, so if you don't want to show up, feel free to turn off your cameras. There will be time for a Q&A at the end of the presentation. So please write down your questions in the chat, or if you would like to ask them live during the Q&A, you can raise your virtual hand and you will have the opportunity to ask questions directly there. So yeah, with that being said, thank you so much for making the time, Gwendolyne, and the floor is all yours.
Thank you, everybody. Hello, and welcome to my talk. I would like to introduce to you happily the Biotechnology Space Support Center, and one of our projects there is called the Cimon project. So thank you very much for this opportunity to tell you about our exciting work at BIOTESC and what we're doing, who we are, and this you would see in my presentation. So this would be the overview of my talk. So it will be in two parts. So firstly, I would introduce to you our group, the Biotechnology Space Support Center, who we are, what we do. And then after that, I chose one project which is close to me because this is actually the bulk of my work at BIOTESC at the moment. So this is the Cimon project. So I will give you an introduction about it, so what it is, or what we do about it, and who are the people involved in this project as well. So, okay, now I start. So the Biotechnology Space Support Center, who we are, what we do. So firstly, I'd like to give you a historical background about it. So in 1977, this is the Space Biology Group, founded at the ETH Zurich by Dr. Augusto Cogoli. And its first space mission is actually immune cells in the space lab in 1983. And then in the year 2000, the European Space Agency and the Space Biology Group signed a contract for the creation of the Biotechnology Space Support Center, or BIOTESC. And then since 2004, BIOTESC has carried out over around 40 to 50 missions to the ISS. And so with our support since 2013, we have been also supporting not only the biological experiments, but also the EAST education program and several other standalone payloads. And now also in addition, we have the operations of technical and technological payloads such as AstroPi and Cimon, and this is because of the increasing diversity and expertise of the team with technical backgrounds as physics, engineering, and informatics. So now actually the Space Biology Group and BIOTESC is a part of the Institute of Medical Engineering of Hochschule Luzern. So this is the University of Applied Sciences and the Arts here in central Switzerland. So I would like to tell you what is a user service and operations center is. So this is actually these are national centers distributed around Europe. So you see here several of the centers. So actually it used to be several of us, However, some of it has been transformed into some other centers. They're no longer USOCs, but are the nature of their tasks evolved differently. So we have here those from Cologne, the MUSC, BIOTESC here in Switzerland, CADMOS in Toulouse, the BUSOC from the Belgium USOC, and then the Spanish USOC, the one in Madrid. So these are centers responsible for the use and implementation of European payloads on board the station. And we act as the focal points among scientists, payload developers, among interagency coordination, and of course, when we support the astronauts on the space station. So we provide scientific, technical, operational support, and these are coordinated by the Columbus Control Center in Munich. So those are primarily our tasks. This one's listed here. So this is the BIOTESC team. We're not actually a very big team, as you see. And although we are a diverse mix of biologists, biochemists, medical and mechanical engineers, physicists, and informatics, those are the expertise within the group. And I think that's where our strength comes from. And yeah, so this is the team. And in the next slide, I have here a video, sneak peek at our facility in Hergisville. Let me see how I could. So this is the BIOTESC facility in Hergisville, just to give you a virtual tour. So these are the payloads that we have flown in space already since the beginning. So we also develop sometimes like payloads such as Astropy, part of the development. This is the cell culture lab. And this is the yeast lab. So we also do research on yeast bioreactor. And we have like our ground-based facilities as well. So we have there several random positioning machines where we simulate microgravity environments. So before we do some other, so this is our random positioning machine. And these are some of the payloads that we flew with parabolic flights. And this is the cubic facility and incubator, which is the ground model, which is very similar to the model we have on orbit the station. It's an incubator where we put biological samples. So we do here tests, ground tests, and simulations. Oh, this is the Cimon. And the Astropy. And this is our control room at BIOTESC. So you see from our window the Pilatus, which is kind of the landmark here in central Switzerland. And there, the sneak peek on BIOTESC. Oops, I'm sorry. So what do we really do at BIOTESC? So primarily our mission is to support experiments on the International Space Station. So I'm sure everybody knows what it is. This the ISS, what it is, and it's an artificial satellite in low Earth orbit, specifically at 400 kilometers, and it is a collaboration among different agencies such as NASA, Roscosmos, JAXA, ESA, and the Canadian Space Agency. And it serves as microgravity and space environment research platform for scientific research, such as in the field of astrobiology, astronomy, meteorology, physics, and some other fields. So in particular, we do our experiments in the European module called the Columbus module. So you see here the Columbus module, and this is actually where most of the European experiments are performed, and particularly in the experiment racks, or the international standard payload racks as we call them. And for example, they have there the Fluid Science Laboratory, the European Physiology Module, the Biolab, the European Drawer Rack, and the European Stowage Rack, to name a few. So as I mentioned, our primary mission is actually to have a successful and smooth experiment execution by the astronauts. And yeah, somehow we want not to hear the phrase where an astronaut would say, "Here, this wheel, we have a problem." So we would like that with our preparation and implementation, before we perform an experiment on board the station, we have this in mind, that we wish or we aspire to have a successful and smooth experiment execution by the astronauts. And how do we do that? So we have different mission phases actually. So it's very important to prepare very well. And it has different phases how we could do that. So firstly, of course, we are already involved in the review process. For example, in the evaluation of scientific specifications and industrial hardware payload designs, to guarantee that an experiment will be feasible on orbit. So operationally and scientifically, that this is a possibility to be able to have at least a guarantee of its success. And then we do a lot of planning and coordination in the development of the experiment and the individual activities of the astronauts. So as I mentioned, we are like a focal interface among the scientists, the payload developers, engineers, different positions within ESA, such as safety, security, and also interagencies we collaborate with, such as NASA or CSA, or JAXA or Roscosmos. And for sure, we do a lot of documentation as well. We write a lot of things like the blueprint, which we call the mission operations and implementation concept, where we have there everything we have to do from the launch of the experiment, how we execute the experiment, the on-orbit execution. So these are all written there, all the what-if scenarios that we may face. And of course, the tests and ground simulations, these are very, very important for the success of the mission. And we can only go to a real-time execution of the experiment when we can declare that these tests on ground are successful. So we do a lot of pre-tests, engineering tests, and end-to-end tests of all the processes and steps.
Yes.
That we have to do with all the involved teams, such as the scientists, payload hardware developers within ESA and other collaborating agencies. And of course, when we are already on the execution phase, so we are in the control room. So this is what we call the real-time ops. And we support the astronauts real time. And together with the flight control team in COLCC, we coordinate together how to successfully execute an experiment. And of course, this one will not happen without any simulations before that too. So even how we coordinate together, we have to have a certain certification before we can be able to support on console, as we call it. And then after that, long process, and then we have the delivery of the data to the payload principal investigators. And these data are somehow pre-analyzed by us, and we deliver them in either in its raw or processed form, and sometimes including the reports. And as a whole, of course, we always have to make sure that all these mission phases are achieved in each of its step. So just to have a breakdown of what we do in our daily activity, for example, maybe you're wondering what does a day consist like when we are working. So one of our tasks and activities is, for example, to plan and implement maintenance activities and experiments to our facilities and payloads. So these are example of the payloads that we support at BIOTESC, and actually our projects are kind of categorized into three. We have the biological experiments, and this is actually kind of the prime bulk of our activity or the projects that we have at BIOTESC. We have the technical payloads and experiments. We have the AstroPi and Cimon, and of course the educational payload operations. So these are when we prepare like simple experiments for children and students which are from the ESA member states. So here we have I mentioned already this BioLab facility for the biological experiments, and the Cubic, an incubator, the AstroPi, it's a small computer. It's actually a Raspberry Pi computer, which was installed in 2015. And it has several features with which we have, for example, the coding competition among students within ESA or also from other countries. And here they could make a code, and then we execute their codes on board the station. So using all the features from AstroPi. And of course we have Cimon. I will talk about this. So yeah, this is the first one of our tasks, planning and implementing maintenance activities and experiments to our facilities and payloads. And then another task we do is to conduct and carry out experiment sequence tests on ground. So these are end-to-end tests where we test all procedures that we prepared. We also do a lot of testing all the processes, all the timeline, how for example, how much time does it need for an experiment to be executed. So all these things are kind of optimized during these tests. How, for example, the sequence of all the activities we have to do in order that the crew time, which is a very precious commodity on the ISS when an astronaut executes an experiment, that's very, very important to kind of really optimize this amount of time on how much or how to perform the experiment well. So all these things are done within these tests that we have to do on ground. And so here you see us in action when we do the tests on different payloads, and also, of course, before flight, we prepare our samples on site, especially these are biological samples. We cannot just prepare them long time because they have, of course, limited time and lifetime as well. So we do a lot of documentation, as I've mentioned before. So we also do procedures. So each step in this procedure is actually very crucial to also think about its safety, the handling of the payload, how the crew should handle it in a safe manner. And of course, yeah, this is part of us and of our training as well, to be able to do that in a proper way. Another task is, as I've mentioned, we plan the activities for the astronauts. So this you're seeing here on the screen actually are the timeline of each of the astronauts. For example, here we have an ISS commander, one of the flight engineers, the crew themselves. And you see here, like all the activities they have to do, from the sleep to each of the activity they have to perform. And actually, for each one of these activities, these are our tasks on ground to optimize, as I mentioned, how much time they need, and to know all the details about it. We have to give them a heads up if there are some hazard control steps, or to remind them how to do it. So we have what we call execution notes, operational notes, and a lot of other things they have to consider. And all these are intricately prepared by the ground people. And here we also support the crew training of the astronauts. So since we prepared the experiments and the procedures, we have to also help the training team at the EAC when and on how to do the experiment. So may it be a simple experiment, for example, an educational experiment, as I have here with Tomo Pesque on his mission, the Proxima mission before, and with Alex Gerst also. I think this was one of the educational payloads that we prepared. And so during their training, it's part of their training to also be briefed on how to do the experiment already on ground before they launch in space. So of course, after all those trainings and simulations, comes the real-time operations. And beforehand, of course, we perform, to be able to perform a real-time support, we need a certification. And actually it takes long for one operator to be able to support. Sometimes it could even take a year. And we do a lot of training because yeah, the coordination when we are on the loops, as we say, like here you see in the control center in Munich. So we coordinate together with them. And so otherwise, if we will not be able to kind of practice how we talk together, and of course, we want everybody to be on the same page, that everybody has the homogeneous knowledge on a particular experiment. And so we have to have those kind of simulations and testing before we are we are good to go to support the astronaut on orbit. So there, this the first part of my talk. I don't know if you have questions. Maybe we can already discuss, or do you think, David, do we do it at the end of my presentation, or shall I go on with Cimon, the second part?
I think you can go on, and then we have all the questions at the end.
All right. Okay, let's do it like this. So now I'm very excited to share with you the Cimon project. So it's called Cimon. It's Crew Interactive Mobile Companion. And this is the world's first AI-powered companion in space. So it's a project, a collaboration among these institutions, the DLR, the German Aerospace Center, the European Space Agency, Airbus Defense and Space, IBM, and the Ludwig Maximilians Universität in Munich. And it's funded by the Federal Ministry for Economic Affairs and Energy of the German government. So Cimon in a nutshell. So what is this? What is this exactly? So it's designed as an astronaut assistant that will help astronauts in conducting their day-to-day work. And actually, it's one of the world's, or maybe it's even world's first flying artificial intelligence on the ISS. And we deployed it in 2018 and had it as a technology demonstrator during the Horizons mission of the ESA astronaut Alexander Gerst. And actually, it's kind of a very fast-paced project, because within only 2.5 years, the Cimon team was able to achieve and build a robot that can fly in microgravity, that is able to see and map his surroundings. It can hear and understand the interactions of the astronaut. It should be able to reply to a question and display helpful information to the astronaut. So yeah, those are like the basic kind of how do you call it? Like it's like a person. You have like the senses, the common senses. It has it as well. Plus, it's able to fly. So it's a cutting edge of technology, combining many fields of expertise in the fields of the Industry 4.0, artificial intelligence, human spaceflight, human-machine interaction, and Internet of Things, to name a few. So the Cimon features, so it is resembling a head, and its structure is a 3D printed polycarbonate. Its face is an HD display, and if you see here, it's actually a gender-neutral face. You cannot really say if it's a man or a woman. He is able to speak and hear. It can fly through the Columbus module. It's driven by an air-jet propulsion. It has absolute and relative navigation, and its brain is connected on ground via the Watson AI. It has an object and face recognition. You can do verbal commanding, and it's basically a chatbot. So this is Cimon in a nutshell, and just to give you maybe an overview of its parts. Yeah, it has different cameras here. As you see, it has several components. It has 4 cameras around the free flyer to provide visual recording and photography of its surroundings and the crew. It has a display and microphone array for communication. It has here ultrasonic sensors. It has several motor tubes for propulsion in all directions, and also for navigation. And it has some LEDs and laser pointers for visual aid, for example. And it's around 320 millimeters in diameter. It's powered by 2 batteries. And although we can also, of course, power it via a cable. And it has a man-machine interface where you can input by voice and output with its screen or sound. And it has the navigation, guidance, navigation, and control system. So here, I would like to discuss with you further the artificial intelligence of Cimon. So we use the IBM Watson. It has different machines which we can compare to human organs. And for example, to hear, it uses the speech-to-text machine where the received audio is translated into text. And this text is now processed by the brain of Cimon, the IBM Watson assistant. And then the meaning is then transcribed text and now interpreted, and the brain looks for the right reply, for example, which is, of course, again, a line of text. And then it's converted to audio by Watson text-to-speech machine, which is the mouth of Cimon. Cimon has several cameras where he can record videos and photos, but also to recognize objects and faces. These images are processed by the visual recognition machine, and then, which is kind of like the eyes of Cimon. One feature which we have with Cimon is that we have what we call the tone analyzer. So somehow it's like the feelings of Cimon, and it has it's able to steer through the station. So somehow it has body and movement with the GNC, the guidance, navigation, and control system. And I'm sorry. So it's like has a nervous system, the Cimon brain, as we call it, which is on ground. So basically, up there in the station, this is kind of just like an empty ball floating, and everything that it knows, it stays on ground actually, which we are in which we are connected from BIOTESC to IBM Watson Cloud. So here, the different scenarios which Cimon can do. could do assistance scenario where, for example, it could provide procedure instructions to the crew, how to do an experiment. The crew can also use it as a mobile video and photo documentation assistant. You can do a lot of social interaction with it, so you can talk to it on different topics that we train it with. You can do a lot of small talk, and the monitoring scenario where we can collect environmental data, for example, IR light or noise data, the cabin temperature, humidity, and then we have a remote scenario where we can command it from ground. We can send commands into Cimon, and then to control it from ground. And of course, this is the other scenario is very important for the privacy of the crew. We have what we call the offline scenario where Cimon is disconnected from ground. It can keep its position in Columbus, for example, but everything will be cut off. So everything is connected such that the crew can have his privacy, his or her privacy. And then, of course, when it comes to artificial intelligence, the topic on ethics is always like a discussion. And we make sure that since this is one of its kind for now and the first of its kind, we want to do it with certain standards, adhering to policies and regulations. So we have put together measures on how to do that correctly. So the artificial intelligence is professionally trained by the science team members with CITI ethical certificate. The evaluation of the experiment proposal is done by medical personnel, and the astronaut needs to consent to the experiments. So we present to the astronaut what he needs to do, what Cimon will do with him, and what kind of science we are putting together. Then the astronaut will need to have his or her consent before using Cimon on board the station. There are only limited amount of people that have access to the generated data. And there's an oversight of flight directors and medical personnel during on-orbit experiment execution. There's a possibility of cutting the connection between Cimon and the AI on ground. There's also the possibility of the astronaut to switch Cimon offline to ensure the astronaut's privacy. And of course, now we also want to have that with the data handling and management to have our transparency and accountability. So we involve the ESA Data Protection Officer, the ESA Security Control Board, and of course the DLR to have those transparency and accountability for Cimon. So Cimon's link from space. So how is the data connectivity? So it's via it runs through the satellite to NASA. So as you see here, to NASA, and then it goes through the Columbus Control Center at the DLR site in Oberpfaffenhofen. And then the signal travels to us at BIOTESC in Hergisville. And then from us, we connect to the Cimon's brain to the IBM cloud in Frankfurt via internet. And then the runtime of signal is 0.4 seconds in one direction. So round trip of the signal runtime is about a second. And so, yeah, if you see here, one of the very I would not say difficult, but one of the challenges that we had to face is to establish a stable connection from space to ground with Cimon, because as you see here, we have a lot of different channels where we have to go through, and we have to optimize, for example, all the network connectivities from space to ground or vice versa. So here, I think it's time for you to see how Cimon was during its first day on orbit with Alexander Gerst. This was done during the commissioning of Cimon on the 15th of November. That's the first working day of Cimon on orbit the station. So after rigorous preparation, for example, the network test, software update, and system tests, So Alex Durst worked with Cimon and tested most of Cimon's features. So here you would see, I will show you a video how it went on orbit.
Cimon, wake up.
I'm waiting for your commands.
Hello, what's your name?
My name is Cimon.
Cimon, where do you come from?
I'm from Friedrichshafen at the Lake of Constance. It's a nice place.
Cimon, what can you do for me?
I always aim to improve my performance. For that, I will send the survey answers after each experiment down to Earth. But we can also do some small talk if you want to.
Cimon, tell me something about space.
Twice during Mercury's orbit, it gets so close to the sun and speeds so much that the sun seems to go backwards in the sky.
And I'm ready to let it fly. Cimon, do a positive yaw by 90 degrees.
Wilco, positive yaw by 90 degrees.
Very good.
I am happy you like it.
Cimon, can you help me with the procedure?
Which one of the procedures do you want to do?
Help me with the EPO crystallization procedure.
The required equipment is shown on the screen. Are you ready to start?
Yes.
The EPO Flying Classroom 2 crystallization of charged particles demonstrates the charging of nylon and Teflon particles after shaking. Now we can start the main experiment.
What equipment do I need?
Sorry, I am just a robot. I don't know everything you mentioned.
Show me the next step, please.
Start recording on both camcorders. Please tell me if you want to open the referenced procedure.
Cancel procedure.
Really cancel the procedure.
Yes.
Closing the current procedure.
Cimon, play my favorite song.
Yay, I like your favorite hits too.
There we go. He's playing The Man Machine by Kraftwerk. Very fitting. Please stop playing music. Very good. Thanks for that. Ready for next step. Cimon, take a video stream with your front camera.
I'm taking a video with the front camera now.
So this
Okay,
is
I
the
can see the
video
video.
taken by
Sing along those
Cimon.
favorite hits.
But he's still in music mode. Cancel music.
I love music you can dance to. All right, favorite hits incoming.
Cancel music.
What else can I do for you?
If he really likes the music, I understand that.
I understood. Do you like the music? I understand that.
I did shake it before, but he's already playing a video stream. I mean, he's showing the video stream, but still talking about music. Also, he was a bit close to deck. I'll put him back in the center of the deck position.
I'm gonna fast
He's
forward.
just floating there by himself. So I'm not mean. It's sensitive today.
Take a look for when it is time for food.
And he's hungry. He tells me he's hungry. It's lunchtime. So what does a robot eat?
Okay, I think that was already it.
A great demonstration. We like the flying, the attitude hold when it's switched it on. It's actually quite nice. Thanks again to all the engineers involved, and wish you all the best with that data to work on those systems to improve them.
So,
Simon, wake up.
sorry, I need to stop. And so that was actually a 90-minute activity that we have on orbit, and I showed you a part of it. And so I would like to give you also an impression on how we were supporting from ground during this commissioning day. So here's a video of it too. So I am directly talking to the astronaut, to Alexander Gers,
Fly is for him to be aware of his surroundings.
supporting and assisting,
So after which that you detach it,
instructing how to do the Cimon experiment.
please say, Simon, wake up.
Simon, wake up.
Fast forward. So these are the team involved during the commissioning. Simon from DLR, Volker and Christian. Yeah, I think I could fast forward. So just to give you an impression that during this real-time operations, we are
And then for now,
supporting the astronaut directly from BIOTESC.
Yeah, that's great to have Watson interacting with the genes, and then we move to the music.
would be for it to roll 30 degrees to its left.
The long body acted left, but then he's got a little bit of a misalignment that it didn't approach it.
Yeah, so just to give you the
Some music.
impression,
Then
Or
after
to
that, you
see-
can ask him to play your favorite song.
Simon, play my favorite song.
Yeah.
Copy that, and thank you. So now the next steps would be I'll be sending you a series of commands. Send you a command.
so right. So there, yeah, to show you how we do the real-time ops from BIOTESC and yeah, during this day. And so we were able to actually do another mission with another astronaut, Luca Parmitano. And with him, we were able to also introduce one feature of Cimon called the tone analyzer feature. Then on top of that, we commissioned as well the second Cimon, because the first Cimon we had to bring it down. And we launched another Cimon, which is an improved model of Cimon. And so we had to commission it once more. And this actually the Cimon 2.0, which we have now still on orbit. So this is another successful mission that we did in February of last year. So the team behind Cimon actually consists of a lot of people. It's more than 50 people from DLR, Airbus, IBM, LMU, the BIOTESC Hochschule Luzern, and ESA. And this project is the frontier of its development and innovation, but still is a work in progress. And yeah, we were very happy of its outcome that despite it's a fast track project, as you see here, actually our Cimon journey, which was very dense because we had the kickoff only in 2016. And then after that, within approximately 4 years, we were able to do 2 successful missions of Cimon already. And it is one riveting experience. And however complex or fast track space project would be, it's a proof that with teamwork, with the teamwork that we had, with passion, perseverance, and ambition, we can guarantee mission success. And yeah, it was a very, very good experience for everybody. So the upcoming missions that we have, we're preparing for the mission with Thomas Pesquet, who is now on orbit, on board the station at the moment as the ISS commander. We want to do troubleshooting and software upgrade with him and a bit of science as well. Hopefully we will be able to prepare well for this mission. It's actually quite a tight schedule also for us already. And then the upcoming mission with Matthias Maurer, it will be sometime in October. And starting this October, we would like to, with him, to do Cimon education as well. So this will be very exciting because it will be the first time that we will have, we will involve Cimon in the education program for ESA and DLR. So we will be preparing programs for children. And yeah, so hopefully in the future, it will be a deep space companion when we go to further in space. And so on behalf of the Cimon team, we would like to say thank you for everybody who has supported the program, the project. And of course, on behalf of the BIOTESC team and Hochschule Luzern and Hergisbill, we would like to say thank you. And that's the end of my presentation. I hope you enjoyed it.
Thank you very much, Gwendolyne. Thank you for sharing with us what you do. So we're gonna jump into the Q&A. There are a couple questions in the chat already. So the first question I have, can you read them?
No,
I will read it to you if not, if you can't read them. Don't worry. So the first question is, would you clarify what you mean exactly by biological experiments? For example, does it include food-related tests? And how about medical related purposes?
Did you say food?
Food, yes.
Actually, we're supporting, I think, something with nutrition as well. I forgot the name of the experiment. Together with the French space agency CADMOS, I think that this is still in work at the moment. And yes, indeed, so medical experiments such as yeah, for example, the effect of your immune system on microgravity, the effect of muscles on microgravity, different cells in microgravity, like living organisms such as, say, frog cells, or even recently we have what we call the rotiferous experiment. Yeah, for example, the molecular muscle experiment. Yes, indeed, we have a lot of experiments that we support and prepare at BIOTESC for medical and yeah, biology experiments. I hope I was able to answer correctly the question.
Yeah, I mean, I think it was great. I have another question. Do you think that it would be possible in the near future to have Cimon run on an onboard computer instead of using Earth-based Watson capabilities that generate a transmission delay?
Yes, yes, for sure. This is actually in like one of the future endeavors that we are looking at. So when we, for example, have like cloud computing services on board the station as well, then it will be much easier to, I think, adapt those services already on orbit. So of course, when we want to go on deep space missions, the signal runtime, as you see, of course, when it's further from Earth, then it takes much longer. Then, of course, we have to find another way on how we could bring Cimon into deep space missions. So that's actually part of the plans and planning and, you know, ideas that we have already.
Very cool. Could you please tell us about the various challenges involved with this project in using AI, apart from the operational planning and integration of various systems like communications, GNS, propulsion?
So since it's something very new, I would say even the processes, we have to put them together. Yeah, not everything works according to plan sometimes. And the training itself, we have to think. So we do supervised learning at the moment with the AI. So I guess for people working with AI, they know what that means. So that means we put the inputs into Cimon, so it knows. So we have to first plan what do we want with Cimon, what kind of experiment it has to do, things like that. So yeah, at the moment, this is it's not like a very, say, I don't want to say very, very smart. So we know how it is with AI, I guess. But it's still in its baby step, I would say.
Have any results been published already on the performance of Cimon?
Actually, we're the core team of Cimon. We're writing a paper, but we didn't really publish. I think it's still on the process. It was submitted, but it's not published yet. It's under review or something. I don't know.
Okay, no worries. And what's the main difference between Cimon 1 and Cimon 2?
Some of its components, we had to change them because it also has an end of life. For example, with those, some small computers we have inside, we have to upgrade it because, for example, it's only valid for 3 years or so, and then we had to change it. So that's why we had to put another Cimon to upgrade the components.
Okay, but in terms of the AI, there were not major upgrades other than maybe software related.
Software related, yes, we also did a lot of upgrades. And when it's actually the nature of the project to keep on updating it from time to time, of course, when it's still, as you see, it's a very new and on its development as well. So a lot of things we do it also as it progresses. So progressively we fix bugs and we do a lot of anomaly resolutions, things like this. So that's why we always have to update it.
Awesome. So 2 last questions because we are almost on time. What would be the next steps you're looking at to further improve Cimon?
Well, we have a lot to improve at, actually. It's still a work in progress. So we want to have a robust connectivity with Cimon. So as I mentioned, that's already one of the hurdles we had to go through, actually. A robust connectivity, also not only from ground to space, but sometimes also with the AI itself, we have to have a robust connectivity with consolidator, and then with the Watson services, things like that. And the processes are still, we're still putting them together. What else? So yeah, those are what I can think of at the moment.
And just my last question, I'm sure we have students in the audience and they may be wondering what they need to do to get to work and do what you do for a living. Any advice there, like how you get to be support for astronauts on board the ISS?
I guess for me is to have the passion for space and exploration. Actually, that's kind of the unique selling point, the curiosity on what's beyond Earth, and to couple it with your ambition to dream. Yeah, I think something like that, and maybe a technical or a scientific background helps as well.
Okay, well, I think that's a great end to this seminar. Thank you, Gwendolyne. Thank you everyone for joining. Thank you for your questions. And Yeah, I believe the video, I don't know, Candice, you can confirm this, but the video will be available on YouTube later on our channel.
Yeah.
So if you want to review some of the questions or some of the explanations from Gwendolyne, you can do that.
Yeah,
well.
thank you. Thank you to everybody. I'd like to say thank you. I see some of my friends and family connected, and thank you very much for those family and friends. I see them from all over the world, from the Philippines. So hello to everybody. Thank you for connecting.
Thank you, everyone. Bye-bye.
Bye. Have a good day, everybody.
Bye.